Okay, the seventh chapter is equilibrium. In the standard level, there will be two parts, dynamic equilibrium and position of equilibrium. In dynamic equilibrium, you're supposed to define or describe this dynamic equilibrium, okay? So the expected answer will be, firstly, in a dynamic equilibrium, the rate of forward reaction is equal to the rate of reverse reaction. Okay, so this is the first description that they want you to say. And then the second one will be concentration of products and reactants remain constant. Okay, so this one you have to clearly explain to your student. Constant doesn't mean they are the same. They can be the same, but they don't have to be the same. Okay, so they may ask you to like plot, or rather explain in graphical rate and then time. Okay. Okay, so let's say this is the rate of your forward reaction. This is the rate of your reverse reaction. Very importantly, at dynamic equilibrium, the rate needs to be the same. Okay, the forward and the reverse need to be the same. But say you're plotting your concentration against time. Okay, if this is your product and this is your reactant, okay, the graph can look like that. So when the graph becomes horizontal, when the line becomes horizontal, you know that equilibrium has been achieved, okay? But for this, they can also be the same. The concentration at equilibrium can be the same, but most importantly, once equilibrium is attained, the line becomes horizontal, okay? It can also become like, okay, three are possible, okay, for the concentration, but for the rate, they must be the same, okay, when equilibrium is attained, okay? The next one is position of equilibrium. You need to know how to write a KC, which is the equilibrium expression of a reaction. Let's say, for example, I have A amount of A reacting with B amount of B, giving me something like that, okay? So unlike, well, this reversible arrow shows that your reaction is a reversible reaction where equilibrium can be attained. Unlike your rate expression in the previous chapter, which can only be determined through experiment, the KC expression or the equilibrium constant expression of your reaction can be determined just by looking at the equation, okay? So it will be a ratio of the concentration of the product brought to the power of the stoichiometric coefficient over the concentration of the reactants to the power of their stoichiometric coefficient. Okay, so remember that this must be concentration and not number of moles. Okay, later you will discover that in the questions they often use number of moles instead of concentration. Okay, the students may be trapped to using the number of moles to put inside the expression, which can result in the wrong answer. Okay, so if you realize this KC is the ratio between the concentration of the right hand side, product in the right hand side, and the left hand side, okay? So the higher the KC, when you realize that the KC is higher, you will know that the concentration of CR or E is greater than A or B. Okay, the greater the KC, okay? So the smaller the KC, it will be the other way around. So by using Kc, you can know the extent of reaction. Okay, so the higher the Kc, you will know that the reaction is favored towards the right or towards the product, and if the Kc is small, you know that the reaction is favored more towards the reactant. Okay, or we can say that when Kc is really high or a lot greater than 1, you can say that the forward reaction almost goes to completion. But if Kc is really small or a lot smaller than 1, you can say the forward reaction almost doesn't go. Okay, then there will be this principle, Le Chatelet's principle, or where you can discuss the position of equilibrium and how it is affected by a number of factors, namely temperature, pressure, concentration, and catalyst. Okay? You need to also mention to your student that this Kc is always a constant at the same temperature. As long as the temperature is the same, doesn't matter what you change. You can change the pressure, you can change the concentration, you can remove some reactant from here, or you can add catalyst, the Kc will stay the same when the temperature is the same. So you need to emphasize that to your students, okay? If you realize though, these 4 factors are almost the same as the factors that affect the rate of reaction. So in many questions, this also will be tested, okay? So they will ask for the temperature, like how it will affect the position of equilibrium, and how it will affect the rate of reaction. So just take note of that. You also need to know, or rather need to explain to the student about the 2 industrial processes which involves dynamic equilibrium, which is Haber process in the formation of for the formation of ammonia, and contact process, which is the formation of sulfuric acid. Okay, so in this, you have to teach your students what is the optimum temperature and pressure, which will give the highest yield of product, which is the ammonia, and in this case it will be SO3, which is a part of contact process. Okay, so but in actual fact, they do not use this combination of temperature and pressure that will give highest yield of ammonia, and there will be a reason. Okay, because that's because of the kinetics. So you need to explain that also to the students.